All right, welcome back, everybody. So today we are going to start off by continuing our discussion of the support vector machine. And so if you recall, last time we talked about some of the challenges and shortcomings associated with least squares, and we proposed an alternative loss function for classification called the hinge loss, where in particular, the loss associated with a weight vector W would correspond to computing the sum over our n different training samples. And we would look at 1 minus the training label yi and the predicted training label, which we wrote as xi transpose times our weight vector. And instead of squaring this like we would with the squared error loss, we have this little plus sign, which says that whenever what's in the parentheses is positive, we just leave it alone. And whenever it's negative, we set it equal to 0. And then we said that what we wanted to do was to minimize a regularized version of this loss. So maybe I'll just say this is the hinge loss, and then our objective, the thing that we are going to minimize, is we're going to compute W hat is equal to the argument that minimizes this hinge loss plus a regularization term. So minimize sum I equals 1 to n, 1 minus. So we have some regularization parameter lambda times the sum of the squares of all of the weights. And we can also do a kernelized version where we would say that our weight vector W hat would be the arg min over W, sum from I equals 1 to n, 1 minus yi. And now, instead of working with our original feature vector xi, we would map it to a high-dimensional feature space using some function phi and do our regression or our S prediction in that space. Okay, now when we before had talked about kernel ridge regression when we were using squared error, what we said is that there are many settings where this phi vector could be very high dimensional, and we wanted to avoid computing it explicitly, and we wanted instead to use a kernel function. And what we did is we showed how to go from our objective function, again with squared error instead of hinge loss, to an expression that only used the kernel function and did not use phi. And for a support vector machine where we're using hinge loss, we can do something totally analogous, which can be very helpful. And so in order to do that, we need to have a first step that is similar to what we did with the kernel ridge regression. So I'm going to call our estimate here W hat. I'm just going to put an SVM as a subscript here, just to be really explicit that now we're working with a support vector machine. So over here, this is SVM or SVM. So when we are minimizing the hinge loss plus the 2 norm squared of our weights, this is a support vector machine. We'll talk more about where that language and where that name comes from in a little bit. And either of these are support vector machines. In fact, this top one is just a special case where the phi mapping is just an identity mapping. So this support vector machine weight vector that we are going after can be written as a weighted sum of our features, either in their original feature space or in the bottom case, in our high-dimensional feature space. So in particular, recall that capital phi would be our feature matrix in this high-dimensional feature space. And we can write this weight vector, W hat SVM, as phi transpose times some vector alpha. So in other words, our weight vector that we are going after, the solution to the optimization on the first board, is going to be a weighted sum of the rows of this phi matrix. Now our goal is to figure out what that weighted sum looks like, just like we did with kernel ridge regression. But we're going to use this fact in order to find that optimal alpha vector, right? I mean, it only makes sense to solve this by finding alpha if this is true. And so what I want to do now is to show to you that this is in fact true. So this is my claim. And to show this, we are going to assume, for the sake of contradiction, that this W hat SVM cannot be written that way. That actually it's going to be phi transpose alpha plus some extra stuff that can't be written as a weighted sum of the rows of phi. And I'm just going to call that extra stuff W perp. Okay, so let's assume that there's some stuff in this weight vector, in the support vector machine weight vector, that can't be encapsulated using the weighted sum of the rows of phi. And we're going to let W perp represent all that extra stuff. What I'm going to do now is I'm going to show that W perp has to be equal to 0. All right. So in particular, I want to be a little bit more specific. So what we're going to do, we have to assume something about W perp, where W perp is orthogonal to the rows of phi. To the phi of xi's. And that's just I'm just formally stating what I said verbally up here. So the W perp is everything that cannot be represented in terms of the rows of phi. And so in order to say it cannot be represented by the rows of phi, I'm assuming that it's orthogonal to the rows of phi. Okay, so now if we think about our objective function for the SVM, right, what we're trying to do when we try to find the weight vector is we're trying to minimize, again, sum over I equals 1 to n, 1 minus yi phi xi transpose times my weight vector. But now what I'm going to do is I'm going to replace this weight vector with this form that we're interested in. So instead of having W here, I'm going to have capital phi transpose alpha plus W perp. And then I have this little plus indicator for my hinge loss, then plus lambda. And now we've got the 2 norm of phi transpose alpha plus W perp squared. And so if I know that my support vector machine has this form, then finding the best weight vector is the same as finding the best alpha and finding the best W perp. So now I'm minimizing over alpha and W perp, like that. Okay, and now what I'm going to do is I'm just going to unpack this a little bit to make it a little bit easier for us to work with. And in particular, I'm going to write this. Minimum over alpha and W perp. Sum from I equals 1 to n. 1 minus. And off to the side, I just want to remind everyone that when we talk about phi transpose alpha, what this means is I'm going to have the sum So alpha is a length n vector. So I've got the sum from j equals 1 to n of alpha j times phi of xj. So that's what we mean when we write capital Phi transpose alpha. And so I am just going to plug that in right here. And so what I'm going to have is yi, and then in my brackets here, I'm going to have the sum from j equals 1 to n of phi of xi transpose phi of xj, and that gets multiplied by this weight, alpha j. And then I'm going to add to that w perp, so I'm going to have phi of xi transpose w perp. So I've just expanded this out using what the matrix phi transpose alpha means. And then I'm going to have plus lambda. And again, I'm going to have the sum from j equals 1 to n of alpha j, phi of xj plus w perp. Now that I've expanded this out, I see something extremely helpful. So remember that we assumed that w perp is orthogonal to the rows of capital Phi, to all the phi of xi's. Now we can use that information. So what can I simplify using that information at this point? Yeah.
Phi of xi transpose w.
Exactly right. So another way of writing this orthogonality is that phi of xi transpose w perp has to be equal to 0. And so in this expression here, this term has to be equal to 0. Okay, so now we've simplified this expression. Now the only place in this objective function that w perp is showing up is here. Right? So what is the value of w perp that's going to make this whole thing as small as possible? Yeah.
All zeros.
All zeros. Right. So our objective is minimized when w perp is equal to 0. Okay, so in the lecture notes that are posted online, we go through this in a few extra steps. So if it feels like it was a little bit fast to you, the derived notes online, break it down a little bit more. But what we can then see then is that if this is minimized when w perp is equal to 0, then all of a sudden the best w perp is equal to 0. And therefore, the support vector machine, weight vector, can be written as a weighted sum of the rows of this phi matrix, so we've shown our claim. And so now, just like we did when we were looking at kernel ridge regression, we are going to boil our optimization problem down to, instead of directly estimating the weight vector w, we're going to estimate this parameter, or this weights on the samples alpha. Okay, so I feel like I've been throwing the word weight vector around a little bit more than is clear. So I just want to be clear that when we talk about w hat SVM, or even w hat ridge or least squares, this is going to be a vector in our feature space. So either d-dimensional or p-dimensional, depending on whether we have a kernel or not. But it's a weight on our features. So at the beginning of the course, we talked about trying to predict whether a photo is of someone smiling or not. And so we have different facial features. And now we're saying, well, some of those facial features are going to be more important to that prediction than others. So we're applying weights to different features. But the other weight vector that we're working with now in kernel ridge regression and in the support vector machine, this weight vector is in Rn. So it's a weight on each of the different samples. And what we're saying here is that our predictor of a new label for a new training or for a new feature vector is going to be a weighted sum of the labels of my training samples, and we're trying to figure out what those weights should be. And so we're going to derive an expression for that, analogous to how we derived an expression for it in the context of kernel ridge regression. So again, two different weight vectors weighing different things. The W's are weighing features, the alphas are weighing samples. Okay, so now what we're going to do is instead of finding an expression for W hat SVM, we're going to say, let's find an expression for alpha for the weights on samples. Okay, so unfortunately, this is not something that we can do in closed form the way we could with kernel ridge regression. And in particular, we're going to say that alpha hat is going to correspond to solving this optimization problem that we have on the previous board. So it is the argument alpha that minimizes the sum from I equals 1 to n of 1 minus yi sum j equals 1 to n alpha j phi xi transpose phi xj plus the 2 norm sum from I equals 1 to n of alpha j phi of xj. And now I'm going to do a little bit more work on the regularizer here, and we'll see why in a second. So the first part, measuring the data fit, is going to be the same. Oops, and it'll lambda out front. And so now what I want to do is I want to note that within here, I'm computing a bunch of different inner products. And so I can rewrite this 2 norms squared as the sum from I equals 1 to n, sum j equals 1 to n, alpha I, alpha j, times phi of xi transpose phi of xj. And the reason that I've written it out this way is because now we can see that this objective function only really depends on inner products of phis of x's and never explicitly just the phis. So just like we did with kernel ridge regression, we can say this inner product here is the kernel between xi and xj. And here we've got the kernel function between xi and xj. And so we do, just like we could with kernel ridge regression, approach finding the alphas using only the kernels or the underlying kernel matrix instead of ever explicitly computing phi of any feature vector x. All right. Now, unfortunately, when we look at, well, maybe I'll just write this out more explicitly. So our final alpha corresponds to the argument that minimizes over all alpha, sum I equals 1 to n, 1 minus yi, sum over j, alpha j, k, xi, xj, plus lambda, sum over I, sum over j, alpha I, alpha j, kernel, xi, xj. Now, when we were working with kernel ridge regression, where we use squared error here, we were able to derive a nice closed form expression for the alphas. Here, unfortunately, we cannot. The way that we find the alphas is using numerical optimization schemes. And in fact, in the second half of today, we're going to start talking about different schemes like gradient descent. You can use gradient descent on this, but it's not nearly as efficient as other more sophisticated optimization methods that are beyond the scope of this class. But there are existing software packages for solving this optimization problem. But this is what's happening under the hood when we use support vector machines. We are solving this optimization problem in order to get this alpha hat, and specifically the alpha hat for SVMs. And then, just like we did with kernel ridge regression, once we've got the alphas, we can make predictions for new samples in order to get good classification performance. Okay, so let's talk a little bit more. Or, sorry, are there any questions before? Yeah.
Switch the XJ and XI.
I just was trying to talk and write at the same time and wasn't being, there was no reason to switch it. So I've got XI first now every time. That said, I can't off the top of my head think of a single kernel function where it's not symmetric, where the order of the xi and the xj matters. Yeah. Okay, so we've talked a lot about how we compute the support vector machine, but I think I also want to talk about why it's called a support vector machine and what's actually happening here. So in particular, typically, when we solve this optimization, the alpha hat SVM that we end up with is sparse. And by that I mean most of the alpha j's are equal to 0. And there's only a small number that are non-zero. And so if we recall that our weight vector w hat SVM is equal to the sum j equals 1 to n alpha j phi of xj. If this is the form of our weight vector, and most of the alpha j's are equal to 0, then what it means is that this w hat SVM is equal to a weighted sum of a small number of these high dimensional feature vectors. Okay, so we've said all along it's a weighted sum of all n of them, but most of those weights are 0. There's only a small number that are non-zero. And so what are they? So let's make a picture where we're doing classification in 2 dimensions. So I've got feature vector 1 and feature 1 and feature 2. And let me put in some samples. So I've got some negative samples here in the lower left and some positive samples up here. And now I try to derive a decision boundary by computing this alpha hat SVM and the corresponding w hat SVM. And in this space, what I would end up with is a decision boundary that looks like this. It's separating my positive from my negative examples. And just like before, on one side, w hat SVM transpose x, that's going to be greater than 0. And so we would predict for any point in here that the corresponding label is positive. And then on the other side of the line, everything's negative. But in addition to this decision boundary, we can think about the following. We can think about drawing a kind of tube around the decision boundary and trying to make it as wide as possible until we start touching training samples. So in this example, oops, okay, it should be the same width everywhere. I've got this tube here, like I've drawn with the dashed lines. Within that tube, there's lots of different decision boundaries I could have drawn, right? I could just take this boundary here and I could angle it a little bit and I would still have perfect classification on all of my training samples. So there's many different weight vectors that would give me 0 classification error. I'd correctly label all the samples. But the SVM is choosing the one weight vector that makes this tube as big as possible. So to contrast it in orange here, right, imagine that I considered a different decision boundary that looks like this. That's not enough color contrast. And unfortunately, the colors are even less visible on the videos. Okay, so in green here, I've got another candidate decision boundary that among all the ones that I'm searching over. So this green decision boundary is perfectly classifying my positive and negative samples. But if I think about trying to draw this tube around it, that tube has to be a lot narrower. It's a much skinnier tube. And so the idea behind the SVM is that if I consider all the different classifiers that have equally good performance on my training samples, I want to choose the one that has the most padding or the biggest tube around it. And this is to basically try to maximally separate the data. And the idea is maybe pretty intuitive because in this case where I've got the green skinny tube, this sample right here, if it had moved just a little bit, it might have been pushed over the boundary. Whereas with the yellow decision boundary, the one corresponding to the SVM, I would have to move it a lot more before it gets misclassified. And so this SVM classifier that has the biggest possible tube is going to be the one where, in order to start misclassifying points, I would have to perturb them the most. And so this is giving me, hopefully, better generalization performance. Okay, so the technical term for this is not tube, but rather margin. And so in here, I'm going to call this region here the margin. And so what we're doing with the SVM is we are trying to maximize that margin. In addition, I said earlier that this alpha hat SVM is sparse. So remember, alpha hat is giving us a weight on each one of the training samples. So in this example, with the yellow SVM classifier, which are the samples that have non-zero weight? Those are the samples that are right there on the margin, these 3 here. So these are the support vectors. These are the feature vectors that tell me where that margin is located or where that decision boundary is. And those are the ones that are going to get non-zero weights in this alpha vector. Everything else is going to get 0 weight. So for this point here, for instance, the alpha j is equal to 0. And for this point here, the alpha j is not equal to 0. And so when we talk about support vector machines, mathematically, it's exactly like I described before. We're using hinge loss. We're using squared norm regularization. We solve the objective function that I described earlier. But what's happening is that the solution to that optimization problem is the decision boundary that maximizes this margin, and the support vectors are the training feature vectors that have the non-zero alpha weights, and those are the ones that are defining the boundaries of this margin. So in the lecture notes posted online, there are some illustrations that are more complex than this one here, showing much larger numbers of features, and also instead of showing linear decision boundaries, they're showing curved decision boundaries that we would get if we used a kernel. And so you can take a look at that and hopefully build up some additional intuition about this notion of a margin and how the classifiers differ when you vary different parameters or if you vary what kernel you're using, or if you vary this parameter lambda, and it gives you a lot more understanding. Are there any questions?
So for the margin, they are derived by shifting the decision boundary until they meet the sample.
Okay, the question is, are we basically shifting the decision boundary? So I would frame it like this. In our first board here, we said that the support vector machine corresponds to whatever vector W minimizes this objective. So we can think about searching over all possible weight vectors, which is equivalent to searching over all possible decision boundaries. And I'm saying through that search, during that search, we might consider this green decision boundary, but it is not going to minimize the objective function that I described. The one that minimizes the objective function, the one that I've drawn here in yellow, is the one that maximizes this margin. So,
I mean, like the margin is like a margin is like just shifting the decision boundary.
the margin is not shifting the decision boundary. For any candidate decision boundary, we could think about how big that margin is. And we are choosing the decision boundary that maximizes that margin.
But like on the graph, the margins are all parallel to the decision boundary. Can the margins be
Yes.
curved or?
Okay, can the margins be curved? So in this case, so here, in this drawing, my phi function, phi of x, is simply equal to x. I'm using a linear kernel, so I have linear decision boundaries, and this margin that I'm drawing, like you said, is parallel to the decision boundary and straight lines. If I were to use a different phi corresponding to a kernel function, then my decision boundary might be curved and my margin would be curved in the original feature space. But if I were to plot things in my high dimensional feature space, in this phi space, then I would still have linear decision boundaries there and straight line parallel margins there. Yes?
For the support vectors, do they have hinge loss of 0?
Do the support vectors have hinge loss of 0? Yes, that's right. And in fact, the vectors, though, that are correctly classified and are not right on the margin, they also would have hinge loss of 0. So in this case, my data is separable. I can draw a decision boundary that perfectly separates the positive and the negative examples. And so I can achieve, and they're separated by some margin. And so I can achieve 0 hinge loss. So this notion of a margin is a little bit more complex when we have non-separable data, but I'm not going to go into that today, but that is something that's discussed in our course textbooks. Yes?
So basically, I want to ask about, like, for this example, it's very simple, but I mean, like, in real life data, like, I don't think it is, like, very possible that you can have, like, multiple data points on the margin. Like, if you are finding the one which is closest to the decision boundary, maybe there will be only one. So in real life, is it most likely that only negative and positive will only be one data points on the support vector? And also, like, does the margin have to be symmetry, like, on the decision boundary, or they can be not quite symmetry on the positive side and negative side?
Okay. So the first part of that question was, this is a very simple example. Wouldn't it be the case in general that I might only have 1 or 2 samples on this lying on the margin? And the answer is no, because I'm only drawing this in 2 dimensions. But in general, we're in much higher dimensions, and so you do have more more feature vectors that have non-zero weight and that basically are support vectors. So you only have a small number in this case, and it looks a little contrived because we're only drawing this in 2 dimensions. But in higher dimensions, you would have many more support vectors because you need more points to define a linear separator in higher dimensions. The second question was, is this margin always symmetric? Or could it be that it's hitting a couple of support vectors on one side and not, or 1 on one side and 0 on the other side? And the answer is no, that's not possible, because if I had a decision boundary, let's just say that was like parallel to my yellow decision boundary, but closer to the blue points than the red points, like when I measure the margin, I'm looking both above and below the decision boundary. And so by pushing the decision boundary closer to the blue points, I'm making that margin smaller. And so by putting it sort of equidistant from the red and the blue lines, then I'm maximizing the size of that margin. So I'm always having points on, both sides of the decision boundary, if you will.
Can I please clarify? I mean, currently, when we are finding the margin, is that we are somehow to minimize the distance from each data points to the decision boundary.
Maximize.
But we are the margin, the length itself is actually depend on the data point that is closer to the decision boundary, right?
Okay, maybe I misheard you, but I thought what you said is that what we're trying to do is minimize the distance between our training feature vectors and the decision boundary. And I'm saying, no, when they're correctly classified, we want them to be far from the decision boundary. We don't want to draw our decision boundary, say where this dashed line is, so that some of our samples are right on the decision boundary. We want, imagine, for instance, that these are, that these feature vectors correspond to, pixels in an image. You don't want it to be where if you just have a little bit of graininess in your photograph, all of a sudden you change your prediction of whether someone's smiling or not. You want your predictions to be robust to small perturbations. And so by trying to make sure that your decision boundary not only correctly classifies as many samples as possible, but also is as far as possible from any of the training samples, you're providing yourself with that robustness to small perturbations.
But for example, if there's a plus, if there's a data point within the current margin,
yeah,
the margin that will the margin be shorter just because of this one data point?
Yeah. If if my samples were closer together, then I would have a smaller margin.
But it still seems like just one data point could affect our prediction.
Absolutely.
And the rest are not affecting.
Yes. That's right. And that's maybe illustrated with this example, right? These samples out here are having very little effect on where the decision boundary is, right? Because I don't want to change the angle of my decision boundary based on a point that's way out here, nowhere close to the decision boundary. Because no matter how I rotate this decision boundary here, this point is going to remain correctly classified. So if I'm really just trying to make sure that I'm correctly classifying as many points as possible and maximizing the margin, or making sure that my prediction is robust to small perturbations, then I should not be paying attention to points way out here, because I can perturb them quite a bit and their prediction is not the prediction associated with them will not change. That was one of the failings of least squares, is that you could have points that are way out here that were correctly classified, and we were changing where the decision boundary was located based on them in a way that could cause misclassifications close to the decision boundary. So that was a big part of last lecture. That was actually something we want to avoid. And so one of the benefits of the support vector machine is that we no longer have that feature. These points that are nowhere close to the decision boundary are not really affecting, exactly what the angle or rotation of that boundary is. We're really just looking at stuff that is closest to the decision boundary. Yeah. Yeah. Great question. Any other questions? Yeah.
So the margin, like the margin width is just the different, like the width between the two dashed lines.
Exactly.
But if that is it, then aren't we considering the, like balancing the decision boundary inside the margin? Like we want it to be equidistant to the two margins.
Yep. Exactly right. Yeah.
What do the margins look like when your data isn't exactly separable like it is on the board?
Right. So great question. But like I said, we're just not going to go through that in this class. If you're a grad student and still looking for a project, talking about margins and max margin classification for non-separable data might be a fun thing to explore, but it's just not something we're going to go through in this class because now we have just concluded last week's lecture and we're going to start this week's lecture. So we just have a lot of stuff that we need to cover before the end of the quarter. And so we're not going to get into margins for non-separable data. Okay, so what I want to do now is to talk about optimization. And this has come up a number of times. And we're just going to talk about some of the basics. Okay, so in particular, today we're going to talk about basic convex optimization. And next time, on Thursday, we are going to talk about a very important non-convex optimization problem, backpropagation for training neural networks. Okay, so today I really want to get through some of the basics of convex optimization so that we can hit the ground running on backpropagation on Thursday. So in particular, what we're interested in is the following. So our goal with optimization in general is to find some point W, and I'm just going to call it W star, that is the argument that minimizes overall W, some loss function L of W. And so this could be hinge loss plus squared norm regularizer, like with an SVM. This could be squared error. This could be ridge regression. It could be any number of different things. But we've defined how we're going to measure how good a weight vector W is, and now we want to find which weight vector minimizes that loss. And today we're going to focus on the setting where this function L is convex. And we touched on this very briefly in the context of least squares when we were talking about positive definite matrices, but it's a much more general concept. So to define it more precisely, a function L is convex if I look at that function and evaluate it at some W, and that is greater than or equal to that function at some other point V plus the gradient of that function at W transpose times, I just want to make sure I get my signs right, W minus V. And this has to be true for all W and V. And I'm assuming for this that just like we've done with every example in this class, we're considering all W's in p-dimensional space. So if we had more constraints on what W's could be, then this would change a little bit. We're just going to consider the case where we're optimizing over all possible p-dimensional vectors. And so this is what makes a function convex. Now this is an abstract definition. So first let me just verbally say that this means that L is above all of its tangents. And this is something that we can show in a plot. I'm just going to give myself a lot of colors and space now to illustrate this. Ready? Here we go. did white go? No. All right. So let's consider the example where L of W is equal to y minus xw, which we've considered before, where the columns of x are linearly independent. So this is a convex function, as we talked about before. And in this setting, we know we've derived that the wave vector that solves this optimization problem is equal to x transpose x inverse x transpose y. Okay, but now what I want to do is I want to think about this definition of convexity in the context of this example. So imagine that W is one-dimensional. So we just have one W here, and then we are going to plot L of W. And here's my function. And so in this picture, right here is W star. And now if I think about my definition of convexity, I should be able to choose 2 points. And I want this to, I'm going to choose a point here. That's my V. And another point here, which is some other W. Not necessarily W star. And for V, I can look up here, and this is L of V. And I can also look up here, and this is my loss at point W. Okay, so I've got 2 points and 2 losses. And now what I'm going to do is I'm going to draw a tangent line right here at V, L of V. And so that tangent line looks like this. So in green, I am plotting the function L of V plus the gradient. Did I do? Yeah, so I'm sorry. Shoot, it's going to mess up my video. This is V here. Okay. L of V transpose W minus V. So the slope of the green line is my gradient or derivative at V. So I've got this, my tangent has the same slope as my function, as tangents do. And I have then offset it by L of V, so it's the right height, so it's touching my function right there. And now for any point W, let's just call this thing f of W. So my green line is f of W. And remember we said that when L of W is convex, or maybe I'll call it FV of W, then this loss, L of W, is going to be greater than or equal to this FV of W. And so in this picture, we are seeing that because what I've got right here at W, this is FV of W. And so I've drawn my tangent at point V, and now for any point W along here, my function in white, my loss, is above that tangent. And this has to be true, like I said, for all V and W. So no matter where I choose this point V, no matter where I put my tangent, my function in white always has to be greater than the tangent. Okay, so this is all actually true even when we don't have squared error loss. So this example is an example function that is convex and where we know what W star is. In terms of the definition of convexity, this picture is hopefully giving you a little bit of intuition about what that definition means. So we've said before that it roughly is bowl-shaped, and more formally, when we talk about that, we mean that no matter where I draw a tangent, my function is going to be above that tangent. And so I can also do something similar to this in 3 dimensions, though it's quite a bit harder to draw. So I could have a function like this. So this is supposed to be sort of a bowl-shaped function here. So here would be my W star. So my axes, here I've got W1 and weight 2. And my vertical axis is the loss of these 2-dimensional weights. And there's some point in this plane, W star, that corresponds to the minimum. And so again, what I can do is I can choose any other point V, and I can look at my function at V, and then I can try to make a tangent plane at that point. This is where the drawing gets a little bit harder to see. But the point I'm trying to make is that when my function in white is convex, then when I draw that tangent plane, the whole function in white is above that orange tangent plane, no matter where I look at that tangent plane, or no matter where I look at the function. In contrast, if I were to have a non-convex function, so over here, I will draw, I'll just do this in 1D. So I've got W and I've got non-convex L of W. And so here's my function. So now if I were to look at a point, let's say here, V, and I try to draw a tangent line to the function there, then I'm looking at the derivative to choose my slope, and so I get my tangent function like this, and I can see that there are many places where my function is below that tangent, and so this is not a convex function. Good? Okay. So now what we want to do is we want to say, when our function is convex, how do we find the minimum of it? And what we are going to do first we're going to talk about gradient descent. Okay, so we're going to consider settings where L is convex. People will use gradient descent even when L is not convex, and we'll talk about that a little bit more at the end of the lecture. And so, most generally, what we are going to do is initialize with some initial guess W, and then I'm going to put in a superscript here of 1, where the superscript is going to correspond to my iteration. So at my first iteration, my guess of the optimum is W1. And then what I'm going to do is the following. So for T equals 1, 2, 3, maybe forever, I'm going to update this guess So I'm going to compute my weight vector for the t plus 1 iteration by taking my weight vector at iteration t and making an adjustment, and in particular by taking a step in the direction of the negative gradient. So I take my loss function L and I compute its gradient with respect to W, and I evaluate that gradient at wherever my current iterate is located. And that's really it. And then I look and I see if I should stop. So for instance, if WT and WT plus 1 are close, then I would stop. In this, I have tau. Tau is a parameter greater than 0, and we call this the step size, or sometimes people will call it the learning rate. So the gradient L of L evaluated at W is telling me in which direction to change my weight vector, and tau is telling me how big of a step or how big of a change I should make. So let's first look at a special case of this for our least squares example, just to be very concrete, and then we will draw a picture of the iterates in a toy example. Okay, so we've got y minus xw 2 norms squared, and if we FOIL that out, we've got y transpose y minus 2 w transpose x transpose y plus 2 w transpose x transpose xw. Okay, so this is our objective function. And as we derived in the past, the gradient of this function with respect to w was equal to negative 2 x transpose y plus 2 x transpose x w. Sorry, there's no 2 here. There we go. Okay, so this is our gradient. And so what we're going to do is we start with an initial guess, W1, and then for t equals 1, 2, 3, etc., WT plus 1 is going to equal WT minus tau, and now we plug in our gradient, which is going to be negative 2 x transpose y plus 2 x transpose x, and now we're evaluating our gradient at WT. We're at our current estimate. Or if it's easier, we can write this as WT plus 1 is equal to WT plus 2 tau x transpose y minus 2 tau x transpose xwt. And then if WT and WT plus 1 are sufficiently close, we would stop. Okay, so this is something that we talked about before, and now we have this much more general expression for gradient descent. And if we make a plot of what's happening here, where W is a scalar now, and my vertical axis is L of W, and so my function is this nice quadratic function, And right here is my W star. This is the thing that I'm going after. Okay, so I'm going to start with some initial guess, W1. And what am I going to do? What I'm going to do is I'm going to compute my new guess, W hat, by first of all computing the gradient of my loss at this point and taking a step in this direction. So in particular, at this point, my loss is sloped downwards. And that tells me that the way I need to adjust my weight is to move to the right in order to make it smaller. And I'm going to compute my gradient here. And that gradient is going to tell me how steep the slope is. When the slope is steeper, I can take a larger step. And so my new weight, W2, would be, for instance, here. And so then what I would do is I would repeat this process. I would compute my gradient at this point. And then I would move in the direction that the gradient is telling me. So I'm still moving to the right. But my slope is a little bit shallower now, which means that I'm closer to the minimum. At the minimum, the slope is equal to 0. Since I'm closer to the minimum, I'm going to be taking a smaller step. It's still scaled by tau, but it also depends on how big this slope is. And so my next step is going to be in the same direction, but a slightly less big step size. And then again, I would repeat this. I would compute my slope at this point. It's a little bit shallower. It's telling me still to move to the right, etc. And I would keep on repeating this until basically the distance between successive iterates is super small, which means that basically my gradient is close to 0, so I'm not moving very much anymore. Yes?
Can you ever overstep to the other side?
Yes. Excellent question. Can we ever overstep? Okay, here's my loss function. And here is my initial point. All right, so now I can have different observations of what happens depending on different W. So I could have, tau. So I could have tau being, maybe I'll just make this red because it's bad. Tau is really big. And we're going to talk about how big is too big in a little bit. So now I am correctly saying from here, I need to go right, but I overstep. And I overstep way too much. In fact, I go so far to the right that my loss function even increases. I'm in worse shape than I was before. And so that just continues and I diverge. Very bad. So I'm doing gradient descent, but I chose too big of a step size, and so I don't actually find a minimum. So that's one possibility. Then I could have tau somewhere in the middle. And I could have the situation that I drew on the other board. But I could also have a situation that looks something, for instance, like this. So I am overstepping, but I'm not overstepping too much. And eventually I do find the minimum. So this is fine. This is not a problem. And then I could also have a tau that looks like that's very small. And then I get this. So I'm overstepping. Or sorry, it's not very small. It's too big, but not so big that I diverge, but still too big. So I've got, maybe wrong order. Tau medium big. So I have to do a lot of steps. Or similarly, I could have tau tiny. And when tau is tiny, I'm going like this. And all my steps are super close together. And so if I do it long enough, I will eventually hit the bottom. I don't diverge, but it takes forever. So okay, so these really make the electric company very happy. And so this is where people spend a lot of time thinking about, well, how do I choose a good step size or a good learning rate so that I, first of all, primarily don't diverge, but also so that it doesn't take forever to converge. I want to do it in a relatively small number of steps. And in fact, when we go beyond gradient descent in optimization classes that you might take after this class, they'll talk about ways in which you can try to reduce the number of steps you need to take in order to reach the minimum or to get very close to the minimum. So there are a lot of things that you can do that can exploit structure in your loss function that can help you find the minimum more quickly with fewer steps. So yes, you can overstep. Overstepping is not necessarily a bad problem like we had in our yellow example. But if you overstep way too much, you diverge. If you overstep too much, but not way too much, then it can just take a really long time to converge. So there's a bit of a balancing act. In the lecture notes, we're not going to have time to go through it in class today, but we can show how big is too big. So there's an upper bound on tau that we can derive explicitly for certain problems, including least squares, that tells us we need tau to be below that upper bound in order to ensure that we're going to find the minimum. And so I do encourage you to look at that because it's using a lot of the different things that we talked about in this class. And has some really nice mathematics involved. Okay. More pictures. So, like I said, sometimes people will try to apply gradient descent to non-convex optimization problems. So for instance, you have a loss function like this. So it can work, right? If I were to choose my W1 here and then do gradient descent, then I might see a series of iterates like this, and I reach the bottom, no problem. But if I had chosen to start, let's say here, and I do gradient descent, then gradient descent is telling me to follow the direction of descent, and I end up in a place that's a local minimum and not a global minimum. So this is a local minimum. So I started off by talking about convexity. And so the key point is if L of W is convex, then we, for tau not too large, we are going to find the global minimum no matter where we start. So we don't have to really be worried. So in this case, this is the global minimum. And when we've got convexity, we don't have to worry about how we initialize. We're always going to wind up at a global minimum. If it's not convex, though, like in my picture, then where you minimize or where you initialize will make a big difference. Okay, There's some additional illustrations and examples in the lecture notes that I really encourage you to look at. They're pretty. They also talk a little bit about how we can think about the shape of the loss function for least squares using the singular value decomposition that I think gives some nice intuition. But in the last few minutes here, I want to talk about a core tool that we are going to use for backpropagation, and that is stochastic gradient descent. The idea is very simple. So we are going to consider the case where we can write our loss function L of W as being an average over a bunch of other little loss functions, Li of W, let's say n of them. So for instance, this could be if L of W is just our squared error loss. We could write this as 1 over n, the sum I equals 1 to n. I do this right. Or, I'm sorry, if our loss function was 1 over n out here too. Of yi minus xi transpose w squared. And so in this case, this is what we would call Li of w. So we're thinking about our overall loss as being a sum of little losses over all of our different samples. Okay, we're not really doing anything different, but what stochastic gradient descent is going to do is the following. So first of all, regular gradient descent, we can write in terms of these mini loss functions. So we've got Wt plus 1 is going to be Wt minus tau. And now we're going to have divided by n, sum I equals 1 to n, of the gradient of all of our little individual loss functions. Okay, this is equivalent. I'm just plugging in the fact that we've got multiple loss functions that add up to give us our overall loss function. Okay, or just want to make sure I'm doing my 1 over n stuff. Yeah. Okay, so that's what regular gradient descent does. And now when we talk about stochastic gradient descent, what we're going to do is we're going to only use one sample at a time. So at iteration t, we are going to select a sample I sub t. And then what we are going to do is we are going to update our weight vector, Wt plus 1, to be Wt minus tau times the gradient Lit of W at t. So all we're doing is instead of doing gradient descent with all of our samples at each step, with stochastic gradient descent, we're going to choose one sample and use it to update the weight vector. And then at the next iteration, we choose another sample and we use it to update the weight vector. This can be helpful if we've got huge data sets. So for instance, when OpenAI is training ChatGPT's neural network, right? They've got billions, maybe even trillions of training samples. And so every time they want to update the weight vector, loading all of that into memory alone is a huge amount of computation. And so what they're doing is they are just loading a subset of the data into memory at a time and making updates based on that. Okay, so this can give us big computational savings. And so there's a couple of variants of this. And when people, let's see, one version of this would be what I would call random permutations. And by this, what I mean is that every n iterations, I'm going to reshuffle my samples. So for instance, if n were equal to 3, so I've got 3 training samples, then my sequence of ITs might be equal to, 1, 3, 2. So I do 3 rounds. I hit each sample once in some random order. Then I'm going to reshuffle them again. Now I might get 2, 1, 3. So that's my second epoch or round across all of my samples. Then I reshuffle again. Now maybe I get 3, 2, 1. That's my next epoch. And so what I'm doing is I'm making sure I'm hitting every sample exactly the same number of times, but I'm shuffling the order every round. So this is one common mode that people work in. This is what I see a lot in practice. When it comes to theory and proving these things converge, and that you're actually going to find the minimizers of your loss, it's much easier to work with a purely stochastic version. And so how did I refer this? Yeah, just choose IT uniformly at random. And so, for instance, when n is equal to 3, my sequence of ITs might look like 3, 1, 2, 2, 2, 1, 2, 3, etc. And so here, because every round is independent, the choice of sample that I use at each round is independent of all the other rounds, theoretically it's a lot easier to analyze. But in practice, people maybe use it a little bit less often because it's possible that we use some training samples many more times than other training samples. Whereas the random perturbations or random permutations give us assurances that we will always see each sample the same number of times. Okay, so there's some additional notes in the lecture notes that are posted online. So online, we've got guidelines on tau and some theory about proving that these things actually converge. There's also information on the loss function geometry and the singular value decomposition that ties a lot of things together. And then, in addition, mini batch optimization. This is used quite a bit in training neural networks. So with stochastic gradient descent, we're only looking at one sample at a time. With mini batch, you might say, I want to look at 10 samples at a time. And so I kind of lay that out explicitly in the notes. Please do take a look at that, because on Thursday, we are going to hit the ground running with backpropagation for neural networks, which uses stochastic gradient descent. So make sure this is solid, and I will see you all on Thursday.